Greetings and welcome. It is Dr. Wood again here talking about hypothesis testing. So what is our hypothesis? Again, you guys have mostly already come up with the hypothesis, right? If you did your research proposal, you've already developed one of those. Remember, the hypothesis is what we think is going to happen within a piece of research, right, or an experiment. Remember, these need to be developed a priori, meaning they need to be developed before you actually go into the research itself. You can't get halfway through the study and then be like, well, I think this is probably going to happen based off what I'm seeing. That clouds your results. That introduces too much bias. And so this is going to be important to make sure that to not cloud your results and make sure that you're including all this stuff done beforehand, right? So again, this is why I wanted you to come up with a hypothesis for your research paper before you actually do the research to find out what you're going to see out there. Okay, so again, there is a little bit of method to my madness. Not much, but just a little bit. So again, this is what you think is going to be what you're going to find, and then that should compare back to the null hypothesis. So as an example, if you think, well, I think this new drug regimen is going to help lower blood pressure better than the other stuff, then you would say, well, my null hypothesis is that there's no difference and they would lower blood pressure the same as all the other drugs. So again, it's important to know the difference between your hypothesis and what the corresponding null hypothesis would be in that case. So remember, when we say that we are finding statistically significant results, that's basically saying we're going to be rejecting the null hypothesis. Rejecting that null hypothesis means there is a real difference between the groups that we're comparing there. When you fail to reject that null hypothesis, it doesn't mean that there's no difference between the groups. It just means that we couldn't find it. Remember, when you're trying to achieve a p-value of less than 0.05, that doesn't mean that you find, if there is a real difference there, you're going to find it every single time, right? There's still a 1 in 20 chance where you're going to find erroneous results. And so in those cases there, just because you fail to reject the null hypothesis doesn't mean there's no difference. Usually what you're going to find is that most studies tend to be underpowered, meaning that they don't have enough study participants to actually show that there is a true difference based on the effect size that you're really looking for. So for instance, if you're trying to find, say, a new drug that can lower blood pressure, say 20 millimeters of mercury greater than what the competition is, you may need a lot of patients before you could find that sort of result. And very frequently, you'll find that a lot of studies you're going to be looking at will say, well, we were underpowered to really show the differences here. So just because they don't show anything significant doesn't mean that there isn't a real difference there. They just couldn't find it themselves. Now, hopefully some of you remember the errors that can happen here when performing these studies. So for instance, let's say we have here, let's say we have our null hypothesis, which is true, and we have our null hypothesis is false, right? The H0 basically means our null hypothesis. And we can either reject the null hypothesis or we do not reject the null hypothesis. Okay, so let's look at this here. Let's say we have something where the null hypothesis is true. There really is no difference between our groups here, but we perform our study and we find some significant results. So we would go ahead and reject that and say, look, there's a difference here. I reject the null hypothesis. But it's not true, right? We know that because we just said here the null hypothesis is true. That is a type 1 error. That means you're getting a false positive error. You're saying there's a difference, there's really not one there, okay? Now again, there's no easy way to tell if your studies are looking at are going to have a type 1 error, but just know that is a possibility. Every study you look at out there, if they show something significant, it could just be random chance that they're finding that, right? When I say a p-value less than 0.05, that still means a 5% chance that is just due to random error, okay? So always keep that in mind. Now, however, if we have the null hypothesis being false and we say that there really is a difference between the groups and then we reject that, then that's a correct decision. That's all well and good, okay? On the flip side, let's again say that our null hypothesis is true and we do not reject it. We don't find any difference between groups. That's all well and good. It's a correct decision there. On the flip side, though, let's say the null hypothesis is false. There is a difference between groups, but we don't reject the null hypothesis. That is, again, where oftentimes studies are underpowered and we cannot find the difference there. That is a type 2 error. It's a false negative, right? Type 1 errors are false positive errors where I'm saying there is a difference and there isn't. Type 2 errors are the opposite, where I'm saying there's no difference, but there really is, okay? And again, this is usually an issue of power, not having enough patience. Type 1 errors are usually going to be more a result of bad study design or bad statistical analysis or just random chance. So, as I mentioned, if you're reading a study They should be talking about sample size, and they should be talking about power in most cases, right? So power calculations are done, and they should be done a priori. Basically, you're trying to determine, okay, what kind of effect size am I looking for? How big of a change in blood pressure, change in blood glucose, change in pain scale, whatever the case may be. You determine that beforehand, and that will help you to determine what kind of sample size you need. Is 30 patients good enough to find it? Maybe 300, maybe 3,000, who knows, right? But that is where the sample size is determined based on the power calculation. As I mentioned, most studies end up being underpowered because, one, recruitment is very difficult. Either patients don't want to sign up, or it's hard to find patients to be willing to sign up. I will tell you, for instance, in a study we were doing on pit viper antivenom when I was doing fellowship, basically the study coordinators were only working during the daytime. So if we had a patient who would get bit by a snake at nighttime, we couldn't involve them in the study. And if you remember, we talked about the 7 T's of snake bites. You remember one of those was tequila. Well, when do most people drink their alcohol and decide they want to pick up a snake and take a selfie with it? Usually at nighttime, right? And so it was hard because we would find that we missed a lot of patients over nighttime just because we didn't have the funds to pay someone to be there overnight on the off chance that someone would get bit by a snake, right? Also, it kind of goes into convenient sampling, say only certain times of the day. So if a patient gets bit by a snake Monday through Friday, and during business hours, they may get involved in the study. Otherwise, they may get missed. Okay, that's usually why studies end up becoming underpowered, or if they just had such an unrealistic study sample size set up beforehand, it may be impossible to reach. Right, especially with really disease states have very small numbers to begin with. Usually, as orphan indications, things like SMA, other things like that, it can be really difficult to find enough patients to even have the disease to involve in the study. Okay. Now, again, you should find that power calculations and sample size should be addressed in most papers, especially if it's a randomized controlled trial, if it's a cohort study, things like that. They should be talking about it, at least addressing it in their methods, and then also in their discussion section. Now, going into multiple comparisons. Now, again, I have a blind squirrel here, and even he finds a nut every once in a while. And basically the point I'm trying to make is that if you keep comparing things, if you keep trying to make different calculations, eventually you're going to find something that will look significant there. And as I mentioned, this is a big problem in terms of type 1 errors, right? So if I keep running different comparisons until I find something, that's not really good study design. You should have all of your comparisons already set up before you start the study. That is, again, a priori. You should be determining that. And you should have corrections in place already. So example, with the Bonferroni correction, basically it just means you take that initial P of 0.05, your significance level there, and you just divide it by the number of different comparisons you're going to make. So as an example, if I were to have, say, 10 comparisons I was going to make, I just divide 0.05 by 10, and so each of my comparisons would have to reach a level of less than 0.005, right? So 0.05 divided by 10 in order to achieve significance. If I was going to do, say, 2 comparisons, I would just take that 0.05 and divide that by 2, and then I'd have to reach 0.025 in order for my results to say they're significant. So because of that, they need to make sure they're taking that into account as well. Because again, I can keep running different calculations over and over again, and eventually I'll find something just due to random chance. But that's not good science, right? That's a type 1 error in some cases, and so we don't want to do that. Okay. I had one student, I'm not sure if it was your class or not, but one student who came up to me and they said, oh yeah, I was an undergrad and I was doing some research with, I think they're doing some kind of fish or something, and they didn't find any significant results. And so their teacher actually said, well, just keep running different stuff until you find something, and that's what we're going to go with. I was mortified, but it probably happens, right? Probably happens a little more often than you think. Because again, who wants to publish negative results? Not me, right? So in those cases there, you may find some bad science being done in those cases there. So you got to be really careful with multiple comparisons. Anyway, that's it for hypothesis testing. If you have any questions, let me know, and I'll see you guys next time. Thanks a lot.